All right, so next we're going to look at composite functions. This is a little different than just adding, subtracting, multiplying, and dividing. This is actually substituting one function into another. And I had alluded to this earlier on, and this is why I told you when you write a function that it's nice to maybe just put parentheses and then plug in what's needed. So sometimes this is called fog of x, right? It's f of g of x, and that really means, there should be another parenthesis here, by the way, plug the g function into f everywhere you see an x, okay? All right, and if we're talking about the domain, then the domain of f of g of x is all numbers in g that are also in f. Okay, so they have to be restricted by both of the domains. Now, these first two are really nice. They're polynomials, so they don't care, right? They're going to be allowing any number from negative infinity to infinity, so we don't have to worry about that so much. The last bullet point here says, in general, f of g of x is not equal to g of f of x. And actually, in the next section, 1.8, we'll discuss when that happens. Okay, so let's just try and see if we can substitute these functions in and see what happens. So f of g of x means f with g plugged in. So I'm going to take the f function and I'm going to write it with parentheses instead of x's. Then everywhere I have a parenthesis, I'm going to substitute the function g of x. Okay. Now I need to multiply this all out. So the first is FOIL. So I have 4x plus 3 times 4x plus 3. And then we have minus 2 times 4x plus 3. Now, personally, I noticed that both of these things have a 4x plus 3 in them. I'd factor it out and then do the multiplication. So actually, I think I might go ahead and do that just to show you just an alternate way to do this. So you could go ahead and multiply this out, right, as such, and then add it all together. But I want to show you an alternate way here. So notice this is something times 4x plus 3 minus something times 4x plus 3. So to me, that says, you know what? Let's take a 4x plus 3 out. What's left? Well, there's a 4x plus 3, and then there's a minus 2. So now I have 4x plus 3 times 4x plus 1. Now I can just do the FOIL for these two, and I'll get the same result as if I had multiplied it all out in the other case. So 4x times 4x, that's 16x squared. Then we have plus 4x plus 12x plus 3. So adding up like terms, I have 16x squared plus 16x plus 3. So this is f of g of x, or sometimes written this way. Okay. What's the domain? Well, we got done saying that both of the original functions were polynomials. They don't care. This is also a polynomial. So they're happy with putting any kind of x in there. All right. What if we did g of f of x instead? So now we're plugging f into the function g. Right? This is g of f of x. So the g function was 4x plus 3. So we're going to do 4 times parentheses plus 3. And inside the parentheses, we're plugging in the function f, which was x squared minus 2x. Here we will multiply the 4 through. And there are no like terms, so this is as far as we can go. This is g of f of x. It's another polynomial, so its domain is minus infinity to infinity. All right, let's continue here. So what does this notation tell us to do? It says f of f, and instead of x, it just means plug in 3. So we're going to treat this way. We're first going to find f of x, which means inside the function f, plug inside the function f. And then when we're done, then we're just, for x, we're going to let it equal 3. Okay? So f of x. Well, the function f of x is x squared minus 2 times x. And in each one of those parentheses, we're plugging in that exact same thing, x squared minus 2x. That is f of x. And then it's just a matter of multiplying everything out. All right, so let's go ahead and multiply this all out. So this would be x squared minus 2x times x squared minus 2x minus 2 times x squared minus 2x. All right, so we got x squared times x squared, that's x to the 4th. Then we have x squared times negative 2x, that's minus 2x cubed. Do that again. And then negative 2x times negative 2x is plus 4x squared. Then distribute this negative 2. Let's add up all the like terms. So I have an x cubed, an x cubed. Looks like minus 4x cubed. Then we have an x squared and an x squared. It's going to be 2x squared. And then finally plus 4x. Now, we were asked for f of 3. So we need to plug in 3 everywhere we see an x. So 3 to the 4th minus 4 times 3 cubed plus 2 times 3 squared plus 4 times 3. All right, so if I did that correctly, I end up with negative 55. So double check me on that. We've got another example here. So this time we are looking at a function that has a square root, which means that's going to cause some restriction on our domain. Remember that square root, the interior must be greater than or equal to 0, which tells me that x has to be greater than or equal to 3 here. All right, what is f of g of x look like? Well, f of g of x is really f with g plugged in. That's the square root of x minus 3, but instead of the x, we are plugging in the entire function of g. Okay. Now, if we simplify under the radical, best we can, we have this. And there's really nothing we can do there. So this is our composite function. And if you wanted to look at the domain of that, you would just set that equal to 0, solve, and go from there. But for this exercise, it just says find the composite function. So I'm going to focus on that. All right. Here we've got g of f and at 4. So that means we want to plug 4 in when we're done. So this is g of f of x, or really it's g of f of 4. So another way you could actually do this is you can plug the number into the original function, then plug that into the new one, and that should work as well. but let's do it this way. So the g function is x squared minus 4x minus 1. And in each one of the x's, we are now plugging in instead x minus 3, which was the f of x function. This is nice because the square root of something squared cancels, and we just get x minus 3 out of that. We can't really do anything more with this guy, right? We can't distribute or anything like that because of the radical. And so best we can do is combine some like terms. And this is our composite function. Now, if we want that evaluated at 4, we just plug in 4. And this is even nicer, right? Because 4 minus 4 goes away. And then we have minus 4 times the square root of 1. And that's just minus 4. All right, so not much to this. What if we wanted to find f of x? Well, this one's kind of silly looking if you write it in one way. All right, so f of x is really f with f plugged in. Remember that f of x was the square root of x minus 3. And so this would be square root of x minus 3. Instead of x, we're plugging in the square root of x minus 3. Now, I wouldn't write it this way. I'd either write it like this, or alternatively like this. Just because you don't see square root of square root very often. I think this is probably the best way to write that. Okay. Again, there's nothing more we can do mathematically here to simplify this. So this is as good as we can get for the composite function of f of f. All right, another example. We've got a new function f and g. We're going to do composites, and this one says plug in -5. So f of g of 5 is going to be, we're going to do f of g of x first. So this is 1 over x plus 1. And for the x, we are plugging in the g of x function, which is 1 over x minus 1. All right, so we have 1 over x minus 1 plus 1. Oops. Got a little 1 heavy there. So minus 1 plus 1 cancels. And I'm just left with 1 over x. If I divide by a fraction, I can flip and multiply. And so I just end up with x here. So this one's really, really nice, right? Because f of g of 5 is going to be plug in -5. I did write 5 here, so sorry about that. It's -5. And that's it. All right, if it's just x, then you just plug in -5. All right, what if we do g of f? Okay. So the g function was 1 over x minus 1. And for x, we are plugging the f function, which is 1 over x plus 1. All right, so 1 over a fraction, you can flip and multiply. So we have this. And then the 1 plus 1 minus 1 cancel. And we get x yet again. So this is one of those rare situations where f of g of x is equal to x, and g of f of x is equal to x. So in this particular case, we ended up with f of g is equal to g of f. And if you remember at the beginning of this section, we mentioned that that's not often, right? So this is actually going to be what we're going to do next, which are inverse functions. Okay. All right, there's one more part to that. What if we want to do f of x? So that's going to be 1 over, and we're plugging in f of x right there. So that's 1 over x plus 1. All right, so I would make the denominator would need to be a common denominator. So we have this plus x plus 1 over x plus 1. That becomes x plus 2 over x plus 1 when you put them together. And I have 1 divided by a fraction, which I can just then flip and multiply, which means I get this. All right, so this last example here is going to be asking us to say, here is a composite function. Can you tell me what two functions make up this composite? So this is fairly simple, right? I see that I have a function inside of a set of parentheses, and it's all to the 5th power. So if I were to define g of x as 3x minus 4, and then I was to define f of x as x to the 5th power, then this function would be f with g plugged in, right? And just confirm that with yourself. So if I take 3x minus 4 and I plug it in for x, that's parenthesis 3x minus 4, close, all to the 5th power. Okay, so this is kind of going backwards from what we've been doing. And this is an important skill that you're going to use in calculus as well, right? Finding what's a function inside of another function. Okay. So here I notice I've got all of this underneath of the radical. So I can let g of x be everything on the inside, and then f of x be the outer function, which is the square root and just of x. So again, if I did f of g of x, right, that would be the square root, and then we'd plug in for x 4x minus 1. Right, last example here. This one's a little harder maybe to recognize. So it's not as simple as saying, 1 over or making it the denominator or the numerator, but you do notice that in common between the numerator and denominator, we have this cube. So if I were to let g of x equal x cubed and f of x then to equal the whole thing, but instead of x cubed, make those x's, then that would also make the correct composite function.